We'll talk about the solutions of our first homework. So let's start. Okay. Let's start with the first question. So in the first question, we ask, a palindrome is a word that reads the same, forward or backward. How many 7-letter palindromes can be made out of the English alphabet? So this question is easy. So a palindrome of 7 letters should be look like this. So we have x1, x2, x3, x4, then x3, x2, x1. So there are 26 possible solutions for x1, for x2 26, x3 26, x4 26. So the answer should be 26 to the power 4. So is everyone okay with this? Yes, okay. And for the question 2, we ask you to prove the following identities with combinatorial arguments. So we didn't emphasize this very strongly in the homework. So if you are not using combinatorial arguments, you may have some deduction in score, but maybe you will still get some score. I will consider it. And so for question 2a, we have n is less than or equal to n, and n plus 1 choose n is always equal to n choose n plus n minus 1 choose n minus 1 plus n minus 2 choose n minus 2, so on to n minus n choose 0. So for the left hand side, we can say n plus 1 choose n is to pick n numbers from 1 to n plus 1. So how do we explain the right hand side? So my explanation is we have n plus 1 cases. For yes, n plus 1. For the first case is the number 1 is the first number which is not selected. For the second case, 2 is the first number who is not selected. That is, we have selected 1 but not 2. So the we have remaining n minus 1 numbers, and we have to choose n minus 1 of them. The third case is similar. We selected 1, 2 but not 3. Then we have to choose n minus 2 out of n minus 2, so on. So is everyone okay with this explanation? Okay.
So for this question, you can have your own story. So it's not, it doesn't need to look like this. Any combinatorial arguments that you find it reasonable, it's okay. It's just one example.
And for question B, we have to choose the summation of n choose k, where k is equal to 0 to n square. Then we have 2n choose k, k is equal to 0 to 2n. So this one is a little easier. Okay. So for the left hand side, we can say this the first we have square and first n choose k from k equal to 0 to n is the number to choose apples from n apples. And the second one is we have n oranges and we want to select any number of them. And for the right hand side, we can say it's the number of ways to choose apples of orange, any number of them. And we have 2n in total. So this should be easy for you. And question 3, part A. Prove the identity using combinatorial arguments. So from the left hand side, we have 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial all the way to n times n factorial, which is equal to n plus 1 factorial minus 1. So how we use combinatorial argument to prove this? So my explanation is, first, the simple side, the right-hand side, the n plus 1 factorial can be regarded as the number of permutations of the numbers 1, 2, 3, all the way up to n plus 1. But we minus 1 here, so maybe we want to exclude one of the permutations. So for simplicity, we say we want to exclude 1, 2, 3 up to n plus 1, the continuous sequence. So for the left-hand side, my explanation is just for each of them, if let's say k times k factorial, this is the longest. Yes, this is the number of sequences such that the longest continuous rising sequence starting from 1 is 1, 2, 3, 4, 5, all the way up to n plus 1 minus k. So why is this? So for example, if maybe I will go with an example first. So if we have n equal to 6, so 6 plus 1 is 7, we want to arrange 7 numbers. And the longest rising sequence from 1 is 1, 2, 3, which is n plus 1 minus k is 3. So how we get such sequences? First, we can arrange the remaining numbers 4, 5, 6, 7. Then we will have 4 factorial possible permutations. Then we want to insert 1, 2, 3 in this sequence, but we don't want to put it before 4. If we put it before 4, the longest continuous rising sequence will become 1, 2, 3, 4. So we want to avoid it. So we have only 4 possible places left. So for this case, we have 4 times 4 factorial ways. So back to the general case. So first, we remove 1, 2, 3 up to n plus 1 minus k. Then we have n minus k plus 1 all the way up to n plus 1. So we want to arrange them first. Then we will have k factorial ways to arrange them. Then we want to insert 1 to n plus 1 minus k back, but we don't want to put it before n minus k, or else the longest sequence will be 1 to n minus k. So we have only k possible ways to insert it back. So the possible number of arrangement is k times k factorial. Therefore, the left-hand side is all the cases of possible rising sequence from 1, excluding 1 to n plus 1. So is everyone okay with this explanation?
So again, you can have your own explanation. So for my case, I'm using a different story.
But is everyone okay with this? Okay. So for question 3b, we find this in the original source. These 2 questions are put together, but this part is less related to combinations and permutations. So we left it with no mark. But because it's very interesting, so we put it here. So we want you to show that any integer n can be expressed uniquely in the following form, where n can be expressed into a1 times 1 factorial, a2 times 2 factorial, a3 times 3 factorial, so on. And for ai should be between 0 and I. So this is very similar to the digit. In binary numbers or decimal numbers, we have something times 10. In decimal number, we have something like a0 times 10 to the power 0 plus a1 times 10 to the power 10 to the power 1, a2 times power of 10 to the power 2, so on. So this is a similar case. So for proving this, I will use the mathematical induction, the simple mathematical induction. But I will try to prove that instead, I want to prove that for any integer n, which is less than or equal to n plus 1 factorial minus 1 can be expressed in this form, and the largest digit is an. So for the best case, n is equal to 1, so we want to show that 0 and 1 can be expressed in this form uniquely. And then we have 0 is equal to 0 times 1 factorial, and 1 is equal to 1 times 1 factorial. So this is correct. This case is true. Then for induction case, so assuming for any integer n prime which is less than or equal to n factorial minus 1, we want to prove the n minus 1 cases. We assume that the n minus 1 case is true. Can be expressed uniquely as this form. Then for the n case n, we have first any integer between 0 to n factorial minus 1 can be expressed as some a1, a2, a3 times 1 factorial, 2 factorial, 3 factorial, and then plus 0 times n factorial. And for any integer between n factorial to 2 factorial minus 1, then we can express as something plus 1 times n factorial, so on. So first, we can finally get k times n factorial and k plus 1 times n factorial minus 1. In this range, we can express it as some a1 times 1 factorial, a2 times 2 factorial, a3 times 3 factorial, all the way up to k times n factorial. So for every two numbers in the same group in here, every two numbers in the same group, they will have different a1 to an minus 1 combinations. And for different groups, they will have different value for an. So for any two numbers, they can be expressed uniquely. So here, the inductive case is also true. So by induction, we can say that the statement, this statement is true. So is everyone okay with this proof? Yes, okay. So for question 4, so we say we have n distinct integers, and we want to choose two groups of integers where the first group have k1 of length and the second group have k2 of length. And k1 plus k2 is less than or equal to n. So in how many ways we can choose numbers such that the smallest integer in the first group is larger than the largest integer in the second group, which means all the numbers in the first group are larger than every number in the second group. So a simple way to select length is, first we can select k1 plus k2 of length first. Then we're picking up the larger k1 integers into the first group and the remaining one into the second group. So the number of possible selections is just simply n choose k1 plus k2. And the second step, we have only one possible way to select length. And for question 5, so how many different 5-letter sequences can be made using the letters A, B, C, D, such that the sequence does not include the word bad? The sequence such as A, B, A, D, D, or B, A, D, A, A are excluded. So the simple way to solve this is, first we find all the possible sequences 4 to the power 5. And then we excluding those include BAD in length. So there are only 3 possible places for a 5-letter sequence to have BAD, only 3 possible positions. And for each position, there will be only 4 to the power 2 of length. So possible sequence including BAD should be, the number of length should be 3 times 4 to the power 2. And we have 4 to the power 5 minus 3 times 4 to the power 2 should be the final answer. So is everyone okay with this? Okay. So for question 6, how many ways can we distribute 2 T marbles among 4 distinct boxes A, B, C, D, such that AB contains at most T marbles, while box CD may contain any number of marbles? So did you receive the letter I sent yesterday? So in this question, we mean A can contain at most T marbles and box B can contain at most T marbles. And because we have only 2 T marbles, that means we can have at the most only one box contain more than T marbles. So the case is easy. So we have 3 cases, and if for the case box A have more than T marbles, then we can have box A have more than T marbles first. So we give box A T plus 1 marbles first, and distribute the remaining T minus 1 marbles among all the 4 boxes. And for box B, it's very similar. So for these 2 cases, we have the number is T minus 1 plus 4 boxes minus 1 choose T minus 1. And if we don't have any restriction, then the number of ways to distribute it is 2T plus 4 minus 1 choose 2T. Then we have the first case minus the remaining 2 cases. We get a final answer, 2T plus 3 choose 2T, a typo, minus 2 times T plus 2 choose T minus 1. So is everyone okay with this? Sadly, there is a typo in my answer. Yes. So for the final question, I will talk here. So consider that we have an unsided polygon, and no 3 diagonals meet at 1 point. Among all the triangles formed by the polygon sides and diagonals, how many of them are there such that the first case, all 3 of each vertex are on the polygon? So to count this kind of triangle, to form this kind of triangle, we only have to choose 3 vertices from the polygon. And it covers all the possible ways of how the 3 sides are formed. So there might be cases where the 3 sides are all diagonals, or one of them is the side of a polygon, or 2 of them is the side of a polygon. They all counted here. So we just have to choose 3 vertices, and that's okay. So we have choose 3 such triangles. And for the second case, 2 of its vertices are on the polygon, and the remaining one is an intersection of the 2 diagonals. So to form this kind of triangle, we have to choose 4 vertices from the polygon. For example, here we choose 4 vertices, and as you can see, this is one of the triangles we formed. But every time we choose 4 vertices, we actually found 4 of the 4 triangles of this kind. So for each combination of 4 vertices, we have 4 triangles. And therefore, the number of them is 4 times m choose 4. And for a third case, only one of the vertices is on a polygon. And the remaining 2 vertices is intersection of 2 diagonals. So in this case, we have to form one of these triangles, we have to choose at least 5, we have to choose exactly 5 vertices. For example, we choose 1, 2, 3, 4, 5, and we connect them like this. And this is one of the triangles we want to find. But for every combination of these 5 vertices, we can actually find 5 such triangles. In this case, it's this star. Just like drawing a star, so we have 1, 2, 3, 4, 5. These 5 triangles. So any combination of these 5 vertices will create 5 triangles. Therefore, the total number of them is n choose 5 times 5. And for the final case, none of these vertices is on a polygon. That is, all the vertices are intersections of diagonals. So for simplicity, we claim that no 3 diagonals meet at one point. So if we choose 6 vertices and draw 3 diagonals, then because these 3 diagonals will not meet at one place, they will form a triangle, like, for example, like this. So for each combination of 6 vertices, we can find 1 such triangle. So the total number of them is n choose 6. Is everyone okay with this question? So
this question is the hardest one.
maybe if we are not counting the next question, but I will not discuss the question today. So is everyone okay with this? Okay. So this is all I have prepared today.
Thank you, Simon.